Okay, so let's look at this here. The limit as x approaches 0 of tan x over x squared. So very quickly, as x goes to 0, tangent is 0, and of course so is x squared. So we are once again dealing with a 0 over 0 limit. So we apply L'Hopital's rule. Limit as x approaches 0, do the derivative of the tangent, should be secant squared x, okay, and derivative of x squared, which would be 2x. So at this point now, as we try to compute it, secant is the reciprocal of cosine, so as x goes to 0, cosine is 1, and so secant being the reciprocal would 1, and then of course squaring it would also be 1. The bottom goes to 0, so we actually have a 1 divided by 0 limit. All right, so that's an infinite limit. Now, to find out what actually happens, we have to ask ourselves the question, because a 1 over 0 limit, or a number over 0 limit, we know is going to be a vertical asymptote. So we ask the question then, as we approach 0 from the right, what is this approaching? Well, as we approach 0 from above, taking on positive values, secant squared, or being squared, secant is positive, and of course squaring it would make it positive. So that's going to be a positive. And on the bottom, 2x, as x is positive, is also positive. So positive over positive means this is actually going to be positive infinity. And then we also look the other way. As x approaches 0 from below, taking on negative numbers, secant then is in the fourth quadrant, where it's actually still positive, but squaring it anyway, so it's not going to matter. It's still going to be positive, but the denominator will be negative, so that will be negative infinity. And so because the left and right are approaching different values, we'd say that this overall limit now does not exist. Of course, the limit's not approaching a number, so it doesn't exist anyway as far as being a number, but remember, if it's approaching the same thing on the left and right, the same version of infinity, then we would say it's equal to that 1. But since they're different, we say that the limit does not exist. And you can see that here on the graph. On the one hand, as I'm approaching 0 from above, you can see the vertical asymptote is going to positive infinity. As I'm approaching 0 from below, it's going to negative infinity. So, of course, the overall limit does not exist since it doesn't approach the same thing on both sides. Okay, let's look at another one before we call it on this video. Let's take a look at our sine x over x, which again I mentioned earlier. We were able to establish using other ways. So this, of course, is a 0 over 0 limit. Right, sine of 0 is 0. Of course, x is 0 is 0. So this is a limit. Now, with L'Hopital's rule, we can differentiate. Derivative of sine is cosine. Derivative of x is 1. And then this is something we can just evaluate. As x goes to 0, cosine is 1. And of course, 1 is 1. Now this is actually a circular argument because actually we can't talk about the derivative of sine without first knowing what this limit is. So actually needed to know this limit in calculus before we could actually talk about the derivative of sine. You might recall from pre-calculus when you learned this idea here with derivatives. It's the right section here. Yeah, here we are. That find him. All right, that when we do the derivative of sine using the limit definition, that we actually needed this limit, right? We needed to know this limit. We also needed to know the other one, cosine h minus 1 over h. All right, we need to be able to compute those limits so we can talk about the derivative of sine. So actually, the fact that I'm now using L'Hopital's rule in computing the derivative of sine, well, I actually needed to know that the derivative of sine was cosine. So I actually needed to already know that this limit was actually 1. So it's kind of a little circular here that I'm throwing it out, because you actually have to know that it's 1 ahead of time before you can compute the derivative of sine. So we're actually kind of using a little bit of circular reasoning here, but we'll just forgive ourselves that for the time being, and just showing you that this is an application of L'Hopital's rule as well.